Le Chatelier's principle, or Le Chatelier's principle, if you prefer. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do DAT, MCAT, and OAT prep as well. I'll leave links in the description for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post one, subscribe to the channel, click the bell notification. All right, Le Chatelier's principle. So not a whole lot of math that we'll be doing in this section, maybe a teeny bit on occasion, but most of this is really going to be conceptual. So but this can really trip students up with a kind of a chicken the egg scenario. But what Le Chatelier's principle really says is that if you place a stress on a system at equilibrium, it will respond to counteract the stress. And so we got to define what a stress is, and a stress is anything that takes a system out of equilibrium. And if you take a system out of equilibrium, it's going to respond to get back to being at equilibrium. That is the fate of all chemical reactions. They want to get to equilibrium, and they're always trying to get to equilibrium. And if they already got to equilibrium, then they're done. So that's kind of the idea. Now we've got to define something else here. And the thing we've got to define is what's called the reaction quotient. And your reaction quotient we alluded to in the last lesson, it's represented by the letter Q. And it's equal to the ratio of products to reactants here in a reaction. So for the one we've been dealing with, and we're dealing with again here, CO squared over O2. And so we have an issue. You might be like, well, Chad, that's the same ratio as K. It is. The big difference is this, though, is that for this ratio to equal K, you have to be measuring these concentrations at equilibrium. Whereas in general, this ratio is always equal to Q, whether you're at equilibrium or not. And so if you're at equilibrium, then this ratio is equal to both Q and K, because that's the point where Q and K are equal. However, if you are not at equilibrium, if a reaction has not reached equilibrium, then this ratio equals Q, but it does not equal K. This will be important. It turns out comparing the value of Q and K is a great way to look at Le Chatelier's principle, but just one of the ways. All right, so if we take a look at what's going on here, we can talk about Q equaling K, and that is true for a reaction that is actually at equilibrium. But what if you're not at equilibrium? So what if Q is equal less than K or greater than K? So then what's the deal? So, well, again, if Q is either bigger or smaller than K, you're not at equilibrium, but you know more than that. You can actually figure out which way it needs to shift to get to equilibrium. So again, we're looking at this ratio of products to reactants, and I'm just going to look at it very generically here. Leave off, any kind of exponents or anything like this, but we have reactant, we have product, and we have a reaction where we've got reactants converted to products. So, and this ratio here can change. As the reaction proceeds, this ratio is going to get closer and closer and closer to equaling K until you finally reach equilibrium, at which point this ratio would exactly equal K. But you find over time, it's going to get gradually closer and closer and closer to equaling K. And so you go from a situation where either Q is less than K or Q is greater than K, and eventually either case, you're going to end up with Q equaling K. So notice, let's start with Q is less than K. Well, so let's say you got K up here and Q down here. What you're going to find over time is that Q is going to grow and grow and grow and grow and grow until it's exactly equal to K. And so in that case, Q's got to get bigger. And so when Q is less than K, it's too small, and it's got to get bigger. And for Q to get bigger, so that reaction has to shift to the right, we say. So you can kind of take a look at this. So what we mean by shift to the right is meaning that reactants are going to be converted into the products from left to right as we normally read a chemical reaction. And so if you notice, what that means in this ratio is that you're converting reactants into products. Well, as you convert reactants into products, you're using up the reactants, and their concentration is going to go down, so your denominator is going to get smaller. And you're converting them into products, so the product concentration is going to go up, so your numerator is getting bigger. Well, if your numerator is getting bigger and your denominator is getting smaller, then overall this ratio is going up. And it's going up again because right now it's too small. It's less than K, and it wants to be equal to K. And the only way that's going to happen is if that ratio gets bigger. And that happens if this equilibrium is going to shift to the right, we say. Now, what if we've got the exact opposite scenario? So where we've got Q greater than K. Well, if we've got Q greater than K, now Q's too big. So K again is here, but now Q is way up here. And over time, we're going to find out that this Q value is going to go smaller and smaller and smaller until the end of the reaction, right when it equals K. And so when Q is bigger than K, that ratio needs to come down. And to come down, we're going to have to convert some products into reactants in this case. So we need to make the numerator smaller and the denominator bigger so that overall this ratio is going to decrease. Well, to turn products into reactants, we refer to that as the equilibrium shifting to the left instead. And so now we've got a great little comparison. If at any point in time I know the concentrations of all reactants and all products, and I measure them, I can look at that ratio of products to reactants, and is it equal to K? Well, then I've already reached equilibrium. But if it's smaller than K, that reaction needs to go in the forward direction and proceed to the right. But if Q is bigger than K, the reaction actually needs to go in the backward direction and proceed to the left. And so now we've got a really good test to figure out which way a reaction needs to go, if it needs to go anywhere, to get to equilibrium. Cool, and that's one way we can look at Le Chatelier's principle. Another way it turns out we can look is just simply by looking at the definition. If you place a stress on a system at equilibrium, the system will the system will counteract that stress to get back to being at equilibrium. That's Le Chatelier's principle. So that'll be another way we can look at it. And so we're going to take a look at a few different things here, but we're definitely going to need some room. And so we're going to look at some stresses, or at least potential stresses, and see what effect they're going to have. And so the first stress we're going to look at is increasing the concentration of O2. Now, the first thing we've got to ask ourselves, is it a stress? And a stress, again, is defined as anything that takes the system out of equilibrium, that removes it from equilibrium. Well, in this case, by adding O2, I change the ratio. And so, again, if the system's already at equilibrium to begin with, then this ratio right now equals K, and it equals Q. By adding O2, it changes the ratio, which means it's no longer equal to K. This no longer applies, but it's still equal to Q. It's just a new Q value. The Q changed. So, again, when you're not at equilibrium, this ratio only equals Q. It does not equal K. Well, by adding O2, what did that actually do to this ratio? Did it make it bigger or did it make it smaller? Because a second ago, it was actually equal to K. Well, in this case, by increasing the value of the denominator, it makes this ratio smaller. So let's kind of take a look at this graphically for a second. And so we're going to have a reaction. And what we're going to have is K right here. And when I increase the concentration of O2, and actually, I guess we should look at this is Q, but this value right here specifically is K. And so it starts out, it's at equilibrium. And at some point in time, we're going to increase the concentration of O2. And by increasing the value of the denominator, it's going to make the overall ratio smaller. And so all of a sudden, that value just went down. And what you're going to find is that this value is going to gradually increase to get back to being equal to K. And so at this point right here, we've got Q less than K. And because Q is less than the K value, because that stress we put on it right there, the equilibrium needs to shift to the right to get back to being at equilibrium. So that's one way to look at this. You figure out, okay, what we did, how did it affect Q? Did it make Q bigger than K or smaller than K, or did it even change the value of Q? And in our case, it made Q less than K, so it's got to shift right. One way to look at it. The second way is using Le Chatelier's principles of the definition. If you place a stress on a system at equilibrium, it will respond to counteract the stress. Well, in this case, the stress is that we added O2. It definitely took the system out of equilibrium because it changed that ratio. And the stress is that now we have too much O2. Well, you only got two options. You can either shift right or you can shift left. Or I guess you can not shift at all if it's not a stress, it turns out. So, but in this case, it is a stress. So shifting right, shifting left. Which one counteracts the stress? Well, the stress is that we have too much O2. If I shift right, it uses up the O2. If I shift left, it makes even more O2. Well, which one's counteracting the fact that we have too much? Shifting to the right. Cool, and shifting to the right is going to cause your Q value to go up. So as you convert reactants into products, till it's back to being equal to K. All right, next stress or potential stress we'll look at is decreasing the concentration of carbon monoxide. And the first question is it a stress? Does it change the ratio? Yes. Then it's going to take the system out of equilibrium, and we're definitely going to classify this as a stress. Now in this case, again, since we changed this concentration, this ratio no longer equals K, it just equals Q. And by lowering the concentration, which is in the numerator, so lowering the concentration of a product, it lowers the overall ratio. And so once again, we just did something that's going to cause our ratio to go down. and it's going to counteract that stress by trying to increase till it gets back to being at equilibrium. Okay, now again, the other way to look at this, again in terms of Q and K, is that by lowering his concentration, we've lowered the value of the ratio. A minute ago, that ratio is equal to K. When Q is equal to K, it was at equilibrium. Since we lowered the ratio, Q is now less than K again, and the equilibrium needs to shift to the right to get back to equilibrium. So, and again, if we use Le Chatelier's definition, the stress is that we've lowered the concentration of CO. It means there's no longer enough CO to be at equilibrium. We don't have enough. So if I shift to the right, I'll make some more. If I shift to the left, I'll use up what I have. Which one counteracts the stress of not having enough? Shifting to the right to make more. So that's how we kind of use the definition there. Now, it turns out one other way to look at this is from a kinetics perspective. So in the last lesson, we said that equilibrium, dynamic equilibrium chemistry, means that the forward rate equals the reverse rate. The rates are proceeding at the same rate. We learned from rate laws in last chapter that rates typically depend on concentrations of reactants. And so the forward rate is going to depend on how much reactants we have. In this case, solids usually, well, I guess solids can affect rates, but we're going to focus on the gas here. So the forward rate is going to depend on how much O2 we have. The reverse rate, though, is going to be dependent upon how much CO we have, the reactant of the reverse reaction. And so when we added O2, it added the amount of reactants we had that were doing the forward reaction, and so it sped up the forward reaction. The reverse reaction for that split second remained unchanged, but the forward reaction just got faster. So if they were equal a second ago, well, now the forward reaction was faster, and the reaction overall was proceeding to the right. In the second case, when we lowered the concentration of CO, again, the rates were equal, but now we lowered the amount of the reactant for the reverse reaction. It slowed down the reverse reaction. And so if a minute ago the rates were equal, well now, because I slowed down the reverse reaction, the forward reaction's faster again. And overall, that means it's proceeding to the right. And that's how we kind of look at this from a kinetics perspective. But whether you look at Q versus K, or just the definition of Le Chatelier's principle from a conceptual perspective, or the kinetics perspective, they should always lead you to the same conclusion. Okay, so now we want to take a look at an important exception that you should realize. And we're going to add or remove a solid. And you might recall that solids and liquids typically don't show up in the equilibrium constant expressions. And so when you add one, it doesn't actually change your ratio. And if it doesn't change your ratio, then you're still at equilibrium. And if you're still at equilibrium, Q equals K, and there's no shift. And so adding a solid here, or removing a solid, will result in no shift in the equilibrium. Not left, not right, no shift whatsoever, because you're still at equilibrium. And so in this case, when we add the carbon solid, it doesn't take the system out of equilibrium, and therefore Le Chatelier would not consider this a stress. Now be careful here, because solids can be affected by a shift, but they can't cause one. So we see here that adding our solid here doesn't shift it one way or the other. However, when we had shifts up here, it would affect the amount of solid present in our container. So in this case, both of these were shifting to the right, and as you shifted to the right in these first two examples, that's going to use up carbon solid. We're going to end up in a situation where there's less carbon solid in our container. And so anything that can cause a shift will affect the amount of solid in your container. So, however, if you yourself add or remove the solid from your container, it itself will not cause a shift. Okay, so keep that in mind. Next thing I want to look at are the trickiest ones of all, and that's temperature and pressure effects. Students get a little tripped up on these, especially this temperature one, as we'll see. And temperature effects, to be able to evaluate those, which way they're going to cause a shift, you have to know if the reaction's endo or exothermic, and that's why I put delta H up here. Delta H is a negative number, and a negative number means it is an exothermic reaction. In an exothermic reaction, the hallmark is that it gives off heat, it releases heat, it produces heat, i.e. heat is a product. And so we can write heat over here, and commonly heat is symbolized by the delta symbol. I could have just simply put plus heat as well, same diff. But the key is I only knew to put heat on the product side because it was an exothermic reaction, since delta H was negative. Had I given you delta H being a positive number, well, then I would have had to realize that that reaction uses up heat, it consumes heat, and heat's a reactant, and I would have had to written it in over here. And so whether it's endo or exothermic will determine on whether heat is a reactant or a product. Whether you raise the temperature or lower the temperature, and in our case, we're going to raise the temperature, that's going to be determining whether or not you add heat or remove heat. When you raise the temperature, you're adding heat. When you're lowering the temperature, you're removing heat. And so when you see raised temperature, you should know, oh, that means the same thing as adding heat. What you need to figure out, though, am I adding a reactant or adding a product based on if it's endo or exothermic? And so in this case, being exothermic, heat is a product. Raising the temperature then for this reaction right now means adding a product, not adding a reactant. And so in this case, it's going to do the same thing as if we just added any other product as well. If we'd added CO instead, it would have resulted in a shift to the left. Notice when we remove CO, it shifted right. If we add CO, the stress is too much CO and we need to shift left to use some of it up. So adding a product here would have resulted in a shift left. Well, adding heat when heat's a product is also going to result in a shift to the left. But this one's tricky. Because if you look, by adding heat, did I change this ratio at all? Well, I didn't. Then you might be like, well, then we're still at equilibrium. Well, we're not. Because if you recall, temperature is the only thing that actually changes the value of the equilibrium constant. And in this case, if whatever you do with temperature causes a shift to the left, like it is in our case, well, that means when you're going to establish a new value for the equilibrium constant, first off, when you change the temperature. And if you shift left, you're going to end up in a situation where you have more reactants and less products than the old equilibrium constant. And so more reactants, less products, that's a lower value to the equilibrium constant. And so what we're going to find is that we've just established a new equilibrium constant for this new temperature, this higher temperature. And so whatever you do with temperature, if it shifts left, that's going to be a new lower equilibrium constant value. If it shifts right, that would be a new higher equilibrium constant value. So if instead of raising the temperature for this exothermic reaction, we had lowered the temperature, well, lowering the temperature would have been removing heat and we would have needed to make more. And shifting to the right with temperature raises the value of the equilibrium constant. So notice all the other changes we've done so far never changed the equilibrium constant. It just changed the reaction quotient Q, and then we had to strive to get back to being at equilibrium. But temperature is the one thing that doesn't change your Q, it changes your K, and Q has to shift to equal the new equilibrium constant. All right, so that's temperature effects. It's super tricky. You got to know which side is heat on based on if it's endo or exothermic, and then you got to know are you adding heat or removing heat based on if you're increasing the temperature or decreasing the temperature. And then sometimes you might have to know, did that make K bigger or make K smaller? And again, with whatever you do with temperature shifts left, K is now smaller. If whatever you do with temperature causes a shift to the right, K is now going to be bigger instead. All right, so pressure effects. So pressure effects are going to be tricky here. And so we're going to increase the pressure. And we're going to increase the pressure by decreasing the volume of the overall container. And that's where things are going to get a little bit tricky. So easiest way to increase pressure. And so you're going to treat these as synonymous. We're going to increase the pressure by decreasing the volume. Cool. Now you might be like, well, Chad, pressure doesn't show up here. Well, but volume does, because these brackets mean molarity. And if you remember, molarity equals moles over the volume in liters. And so even though you don't see volume up here, it's implied as part of molarity. And notice you have molarity squared in the numerator, but you only have molarity in the denominator. And so part of this is not actually going to cancel. So the way this works, when you lower the volume, lowering the denominator of molarity here means you just made the molarity go up. So lowering the volume caused molarity to increase. So by lowering the volume, i.e. increasing the pressure, all molarities go up. And let's say you just, for example, let's say you cut this volume in half. Well, by cutting it in half, you just doubled all the molarities. You doubled this molarity and you doubled this molarity. So it's not equal to K anymore, it's equal to Q. You doubled this molarity and you doubled this molarity. Well, if you double this value and double this value, shouldn't it still be the same number? No, not necessarily, because the top one is squared, the bottom one is not. And so as a result, doubling the numerator and doubling the numerator gets doubled squared. And so overall, your Q just went up in that case. And so as a result, if your Q goes up, you're not at equilibrium anymore. And if you're not at equilibrium anymore, you're going to have to shift. And so in this case, we'll see that, if our numerator went up faster than our denominator, the numerator's too big. So, and again, Q just went up and it needs to get back lower to reach this new equilibrium at this new temperature kind of a thing. Cool. Other way to kind of look at this is that if you have less volume, well, then shift to the side that has less moles of gas, because gases take up most of the volume in your reaction. Solids and liquids take up very little volume compared to gases. Gases at kind of normal, atmospheric conditions take up roughly, 1,000 to 10,000 times more volume than solids or liquids. Molecules are really spread out in a gas. And so as a result, here we've got 1 mole of gas on the reactant side, ignore the solid. We got 2 moles of gas on the product side. And so if you do anything that causes a shift to the right, you're going to end up with more gas and you're going to need more room for more gas. Whereas if you're going to shift to the left, you're going to end up with fewer moles of gas, which is good if you have less room available. And so in our case, with less volume available, less room available, we definitely want to shift toward the side with less moles of gas, which is going to be that shift left in this case. So that's your other way to look at it. And again, if you can reason it out and be like, well, by lowering the volume, we increase all molarities. And if we increase all molarities, the one with the most molarities, in the case numerator versus denominator, is going to increase the fastest. And so in our case, the denominator definitely goes up, but the numerator went up more, so that overall our ratio got higher. And so if the ratio got higher, then it's going to have to decrease to get back to equilibrium. And to decrease that ratio, we got to shift left. Cool, so that one's tricky. Now the last tricky one here is we're going to add argon into our container. We're going to do it at constant volume. So we're going to say that our container is a rigid container. It's not like a balloon where it can expand and get bigger as you add more gas into it. It's a rigid container. We're just adding more argon. And this is going to be tricky because if I put a bunch of argon gas in a rigid container, what's going to happen to the overall pressure? It's going to go up. And you might be tempted to look back here and be like, oh, what could happen over here, Chad, when our pressure went up? Well, here our pressure did go up, but it's because we reduced the volume. But here our pressure is going up not because we've reduced the volume, but I've just added a bunch of another gas. And not just any gas, I added a noble gas. And the key here is that a noble gas is chemically inert. It's not going to react with any of the stuff in our reaction because it doesn't do really any chemical reactions here. And so adding an inert gas, which is typically going to be one of your noble gases, maybe nitrogen gas, N2 gas is pretty inert as well, but most of the time you're probably going to see a noble gas. If you do that at constant volume, it will change the overall pressure in your container. However, you're not going to get a shift. There's going to be no shift, and that might be a little bit tricky, but if you take a look here, by putting a bunch of extra argon in, it did change the pressure. However, by adding a bunch of argon, again, did the volume of your rigid container change at all? No. And if the volume doesn't change, well, the moles of your stuff didn't change either, so molarities are not changing. And if your molarities haven't changed, then this ratio hasn't changed either, and you're still at equilibrium. And so we got to be careful. If you increase the pressure by lowering the volume, that changes molarities, and you're probably going to see a shift. But if you increase the pressure because you added an inert gas at constant volume, that's not going to result in a shift at all. Now, one last thing here, and I meant to mention this back when we went through this. If you increase the pressure by lowering the volume, so it's going to shift toward the side with fewer moles of gas. So less volume shifts to the side with less moles of gas. So higher volume would shift to the side with more moles of gas. It works both ways. So I like correlating your shift with the volume, not with the pressure, because it goes with moles of gas. So volume and moles of gas do the same thing. More moles of gas, more volume. Less moles of gas, less volume. Cool. However, what does it mean if you've got an equal number of moles of gas on both sides? Well, that wasn't our problem. But if you do have an equal number of moles of gas on both sides of the reaction, then your pressure volume shift here is not going to result, or change I should say, is not going to result in a shift. Because again, if less volume shifts to the side with less moles of gas, well, if both sides had equal moles of gas, then how would you know? Well, you wouldn't, because it's not going to shift. And the idea would be that you'd have the same, like let's say these were both squared. Well, then they would both have increased proportionally, the numerator and the denominator, and Q would have still equaled K, and you'd still be at equilibrium. So pressure volume effects will, again, have an impact if you have different number of moles of gas on the reactant and product side. Again, ignore the solids, ignore the liquids, just gases. But if had these been equal number of moles on both sides, pressure volume would have resulted in no shift. And that wraps up Le Chatelier's principle. It can be a little bit tricky at first. I highly recommend you get a fair amount of practice going in. Now, if you found this lesson helpful, that like button lets YouTube know that they should be sharing this with other students as well. And if you are looking for practice, check out my General Chemistry Master Course. It includes over 1,200 practice questions. Free trial is available. I'll leave a link in the description. Happy studying.